Hey, how y'all doing? Yay. Okay, I confer. Okay, good. I've got my last or my only example open that I wanted to have open before we started, and I finished. So hopefully your day is going well or great, or choose the superlative of your choice. I think what I want to do is just the same thing as normal. Start with maybe mentioning one or two administrative things, tackling any questions you might have administratively. Then any subject matter questions, which I suspect today is on the small chance side, and then dive into new content. So that's my plan. And no one's told me they have a better plan than that, but I'm open to it. Okay, so I just gonna share probably a desktop. We'll see what happens. Yeah, looks like that's what happened. And on my screen, it's really, really, really freaking tiny. Okay, but that's fine. I can see my actual desktop that I'm sharing. Okay, so administratively, y'all took a test, and that was good. Now, I think it's fair to say that I will make errors in grading. Sorry, that's going to happen. Okay. Sometimes the way I set up Canvas to auto grade certain questions, there may be an error there. And sometimes, to be honest, when I give partial credit, it's because I wasn't exactly sure, or maybe I misread what you had thought. That was not a joke exactly, but if I'm not understanding what you're thinking and I give you partial credit, and then you come back to me and say, well, look at your answers that you provided and look at this other thing, which, oh, that was tricky. Look at this other thing, which, stop video. Look at this other thing, which I did. So, you provided answers, and I think what I did was really darn close to that. Either you're right, and maybe you should get more credit. That's fine. Argue for points if you want. Or if you're incorrect, which is not unusual either, that means there's probably something subtle that you're not completely grabbing onto in the way that would be ideal. So we could talk about a possible misunderstanding. So always looking into the question of, did I get credit that I think I deserved? That's really worthwhile. Okay. I haven't put the answers online yet. That's probably going to be by tomorrow morning, if not later today. I hope to get later today, but I've got other plans, maybe too, called dinner, and we'll just see what happens. But certainly by tomorrow morning, you should start to check over your answers versus those that are online. We're going to dive in on new material today, and at about this point in time, maybe I should share that these other tests that are coming up, like 2 weeks from a couple days ago, and then on the final exam, just a week after that. Someone always wants to know, is it cumulative? The nature of tests in this class is that they're not intended to be cumulative per se. They're not. However, if you don't know what a simple regression is, or a simple ANOVA, or if you don't remember the general linear model sort of way of parameterizing these categorical factors, some things will be more challenging. They won't be the key part to tackling questions on the next exam or on the final exam, but basically think this way. Exam 1, yeah, by itself, it's just chapters 1, 2, 3. Exam 2, it's chapters basically 4, 5, 6, 7. And exam final, okay, there's 2 parts to it. One of them is on just like 8, 9, 10, 11, okay? And then the other part of the final exam will be more of a across the whole term sort of set of questions. Oh, so one part of the final will be clearly labeled not cumulative, and the other will be, and everything we've done the entire term could be on this part of the test. Okay, so it's going to balance out content from across the entire term in what I think is an appropriate fashion about each check or having about the same weight on the final exam overall. Okay. So I think I've mentioned enough administrative things, and y'all got things down. Oh, one other thing. You know how like labs, y'all turn in labs with groups, etc. I looked and it seems as though you guys haven't signed up for the lab groups. I set them up such that you could just self-assign and go into Canvas and say, hey, here are my group mates. And perhaps I didn't set it up so you could do it easily, but that's sort of what I had expected you would have been doing. And that's not necessarily what any of you did do. And so if you have not gotten credit yet for lab 3 or whatever, don't worry about it. We'll get it figured out. Not a big deal. But if starting with the lab due tomorrow, you actually get yourself into your lab groups, and we're going to stick with the week 2 lab groups, just assign yourself together in the same way that you normally would for those self-assigned groups in Canvas. Okay, so that's my only thing that I'm going to mention. And if you have difficulty with that, just let me know who is in your group and who you want to be assigned into your group, and I can probably manage that at this end. Just an email, copy everyone else in your group on that, and I could manage if you can't figure it out by later today. Okay, any questions about administrative things? Okay, what we're diving into today is, I would say, one of my favorite sections inside GMP, inside our text. It's how do we deal with more than one explanatory variable? Now, admittedly, you could just sort of inside analyze fit model, you could probably do that. You could drag 2 explanatory variables into the model statement. And I'll just go ahead and show you how to do it pretty quickly. So dig up the data I'm looking for. Okay, here we go. Here are data that we'll use a fair amount in class today. And we've got data on a variety of countries. And this is in 1972, the life expectancy of people in that country. And then furthermore, the income in dollars per person per year for people in that country. And then the type of country it was. And the 2 types that we have in our data set are industrialized and OPEC, or petroleum producing countries. So you'd think that perhaps one of these variables or the other, or maybe both together, could explain life expectancy. And I'm going to explore the data sort of graphically at first, and using a tool that will become more and more familiar to you as we go. Well, you've got an X variable and a Y variable. Life expectancy may depend on the income. Good. So there's sort of like a relationship there. And this little curvy fit thing, it's a spline fit. We could talk in office hours if you want to know exactly what that is. But we could make it more closer to straight. We could make it closer to like really wiggly. I don't like that one so much. This seems plausible or reasonable, or heck, even the straight line seems reasonable to me. But I do like the idea of saying there are 2 different country types. With an overlay, we can look at those 2 country types separately. You can spot here, oh, red. There's some red data points that correspond to the OPEC countries. Then blue is the industrialized countries. And in both groups, it's fair to say that there's sort of a slight positive trend, relating income to life expectancy. And it's also fair to say that the industrialized countries have an average life expectancy which is higher than the OPEC countries. And so what sort of a model could we fit? So that's just graph builder. I'm sort of thinking we could tackle the question with 1, 2, 3 different word equations. One is that life expectancy equals income. That'd be a regression. One is life expectancy equals type of country. That'd be an ANOVA or a t-test. And then the third could say life expectancy is income plus country. So I'm going to try and do all three of those analyses. Fit Y by X. No. I want to use fit model. Again, we're starting to use fit model almost exclusively here. Life expectancy depends on the income. We saw a trend, a slope, if you will. Run that analysis, and fit model, it popped up on the other screen here, but I'm going to show you the key parts of the output that are interesting. One is this graph that shows you your data points, and then the fitted trend line. And then if I were to go down a little bit, all the way down to my summary of the fit, you get friends like R squared that you're familiar with, root mean square error. There's the ANOVA for the regression model. And I guess I've got parameter estimates, but I'm going to skip those for the moment. Just graph, summary fit, and ANOVA right now, and that's it. I'm going to do another analysis fit model. Same thing as we looked at before, except I'm going to make a change. Instead of income to predict life expectancy, I'm going to use just the country type. And it seems as though country type, boom, over here, we've got our, well, it's an actual by predicted plot. It's GMP chooses what it presents to you, but essentially because there's only two predicted levels of life expectancy for the OPEC countries, the industrialized countries, you only get two, it's a different looking graph than a regression line, I should say, okay? We do have the grand mean here, then there's this group and then that group, and my summary of the fit, again, that's like your friend R squared is shown to you in your analysis of the fit. And so far we know enough to say, comparing these two, 83% of the variability explained is a bit better than only 57% of the variability explained, yeah? So I think if given the choice, I would choose the ANOVA model with just two groups over the trend model with two groups, and not two groups, with just a regression line. What about the model implied by my overlay of type 1, 2 trend models? Okay, let's go ahead and try and fit that under Analyze, Fit Model. We're going to go ahead and do our friend recall. So life expectancy is, well, type and income. Maybe it's the type, maybe the income, maybe they both play a relationship, okay? Go ahead and run that analysis, and you see in the output shown to you, we've got a 2 trend line model. These 2 trend lines now happen to be parallel. And in chapter 6, we're going to focus a bit more on why they're parallel here. But for now, we're just saying our model is 1 trend line for the blue, 1 trend line for the red. And like before, we've got our friends, our summary of fit, 85%. That's only a little bit better than the 83% we had earlier. And we've got an ANOVA where we say from that analysis varies something. Okay, so first off, what are we saying within that ANOVA? Is there something in my model that's helpful? The null hypothesis for the analysis of variance of a model is something. I mean, the null hypothesis for the model is that absolutely none of the explanatory variables are helpful. Neither income nor the country type plays a role at all with regard to life expectancy. Now, clearly with this null hypothesis having a p-value of 0.0001, even less than that, you'd say, no. At least one of those 2 variables, either type of country or income, at least one of those does play a role. So far, so good? Okay, so the variable plays a role. Yes, it does. The variable plays a role. Yes, it does. At least one of the variables plays a role. We would again say yes. Okay. So did we do a better job in some ways? Well, R squared bumped up a little bit. Here are other reasons why you might want to use a model with multiple explanatory variables. One is it can improve your predictions of y. Yeah, that number MSE, or root mean square error, if you take a root of MSE, root mean square error tells you how far off you're likely going to be if you're trying to predict y with just your x values. So if I've got my 2 trend line model, we're going to have a root mean square error. You could be off by about 4.6 years or so of predicting the life expectancy of a country based on just the country type, OPEC versus the industrialized, and then the income. If you're using just OPEC or not, the type of country alone, you're going to be off by a little bit more, 4.67 instead of 4.60. If we were using, however, the regression only model, your error will be pretty darn big. It's going to be off by 7.5. Okay, so we could reduce mean square error. Also, we're essentially changing the nature of the question a little bit. I would say we're reducing bias here, but that's a little bit more technical. I'll just say we're changing the question. We're no longer asking, hey, is country type gonna matter? We're gonna now ask, having already given income a chance to explain the life expectancies, does adding the type of country into our analysis help us do a better job? Or if we had put country type in first, we would say, now that we already have the industrialized and the OPEC countries, there are sort of 2 different groups, would adding in a slope, a slight trend in each group, allow me to do a better job predicting the life expectancies? It's sort of like a sequential analysis is being done. We already had this model. Do we now want to add a new term to it? Okay. By doing so, we could actually improve the likelihood of spotting a relationship if there really is one. We're changing our question. Really, we're changing the picture. We're increasing our squared. All sorts of real good benefits. Any questions about any of these so far, which will be explained in the examples over the next class session or 4? Okay, so I almost saw a question from Alexandra, but no, that's the thumb thing. Okay, so let's move forward. With the trees data set, you literally can say flowers depend on sex, and we didn't see a significant relationship. You could say flowers depends on the size of the tree, the trunk, if you will, the diameter at breast height. We did see a trend. There is no difference between the male and female trees in terms of the average number of flowers, if that's the only explanatory variable we use. If you say DBH, well, yeah, larger trees have more flowers. Duh, we saw that in the data. Our flowers equals sex plus DBH analysis. That is a richer model, which if you were to try it out, it shows you higher R squared. And always, always, always adding an explanatory variable will not reduce R squared. Usually R squared does go up. Lower MSEs, usually we get better precision. Indeed, it looks as though both p-values for both variables are going to drop, but you're just asking a slightly different question. If we already have DBH in the model, is having sex in the model going to help you? Or if you have sex in the model already, would adding DBH into the model help at all? Okay. I think our friendly geometry, although we've punted on it for 2 of the times when it's come up in the book so far, I want to be sure to go into this guy now, and I'm going to make it bigified so I can draw on it more easily. So I've got this model, and it's almost as though, like Pythagoras, the sums of squares add. You remember Pythagorean theorem, a squared plus b squared equals c squared, yeah? And some of you even are nerdly enough to remember the law of cosines, which is in general, even if you don't have right angle, you have a squared. No, c squared is equal to a squared plus b squared minus 2ab times the cosine of c. Okay, so I just thought I'd show off. Okay, fine. We've got our a squared plus b squared equals c squared. And if you're looking at a block, like I'm imagining one of those blocks that you use when you were 3 in that preschool, right? We've got our distance, if you will, from our data, that's labeled y, your data values, to the mean. That's the average across all the groups. The m point is the sort of like the null hypothesis model, a model with absolutely no explanatory variables. The distance from m to y is like sums the squares y, SSY. So far, so good? Yes. And to find that diagonal distance from the lower left front portion of the block to the upper right rear portion of the block, that diagonal distance, I guess I've got a couple ways I could do it. One way is I could take a compound miter's law and put it at the right angle and chop it right along the MS line. And then we would have the middle sort of such that we could measure diagonally from the point M to the point Y with a ruler. But I'm thinking if I got right angles everywhere involved, I don't have to do that sort of nonsense. I could instead say, aha, if we got a right angle there, we would say that MS, that distance squared, plus SY, that distance squared, the vertical bit, or the diagonal bit, is equal to MY, again, that distance squared. Okay, so A squared plus B squared equals C squared. Y'all remember that guy?
Sure.
Yeah, okay. So what about this MS distance? We could break that apart, and I'm going to sort of go ahead and note, oh, look, we've got D and S. So I'm going to say the MS distance squared equals the DS distance squared plus the MD distance squared. So I could go along the base, first base. Maybe I'll go with green here because then I emphasize the sum here. MD plus DS plus SY equals MY. Okay, so let's write that out. MY squared equals MD squared plus DS squared plus SY squared. So far you're saying, okay, that's geometry. That's a while ago. What the heck does that have to do with our situation here? Well, our data points, not data points, our models here are named and numbered carefully. Notice this M is this mean location, and I'm going to clear that off. And our mean location, again, is a model with nothing in it. D here is a point with just DBH in it. DBH only. DBH only. In this back left corner, which is sort of hard to sort of, okay, so some of you are really good at three-dimensional pictures and thinking and say, oh, yeah, that's the rear left corner. That's the model with S only. And this lower rear right corner is the model of S plus D in it, both. A model with DBH and S in it. And literally, if we got a right angle there, and a right angle there, and a right angle there, I could say to get to my location here, you could either go put in S first, and then D. So that's one pathway. Or another pathway is to put D in first, and then S. Which one should go in first? Which variable should enter into a model first? Well, we're not going to answer that question today. We are going to just simply note that if we put the variables into the model in a different order, you're going to have a different pair of paths that you could take to get to your final destination. I sort of want to do this graphically for you on the next slide. Let's see if we got that. Oh, hold on. Okay, we're going to define our sums of squares. And actually, let's just go ahead and jump into the graph and then go back to the sort of definitional thing. In my model here, where we've got sums of squares, we could fit the mean model, that's the green one here, that regardless of income and regardless of red or black, regardless of whether the country is OPEC or industrialized, yeah, there is a constant life expectancy that you'd expect. So that green line is a model. It says, yeah, income doesn't matter. Type of country doesn't matter. And there is a fitted average value for the life expectancy that you would say, let's imply that all the data points, all the data points should on average have that as their average. And that gives us a bunch of errors. And you could think regression like, you could think ANOVA like, I'm going to think both, because essentially I've got my data points telling me, well, this guy, this individual country is above the average life expectancy of the whole group. This guy is well above that grand mean. And this error here, well, we want to keep track of the errors, and the errors themselves of the data around the model we fit, those errors, if they're big, it says that's a really rather poor choice of a model. If the errors are small, we're doing a great job. The dashed lines, if you will, residuals relative to our mean model, the sum of the squared residuals is that distance. It happens to numerically with this data set be like 34 something. Let's verify that. Actually, hold on. I don't have that ability to verify that real quick, so I'm going to pass on that. I will just tell you. Oh, no, we do have that. Where are the data? Okay, so we go. Let's verify with one of our analyses. So fit y by x. Damn it. No, I want to do fit model. So fit model and life expectancy is going to depend on, and I'm going to fit an ANOVA model with just two groups type. And my total sums of squares, and again, it appeared on the other screen, so I'm going to have to drag and reduce to show you. The total sums of squares is the 3433. Okay, that is the total error around the average, the mean model, if you will. Okay, so that 3433 is the total amount of error we have, 3433. What if I fit a model with income in it? Okay, that would be fitting a trend line where we got a trend line, a slope, if you will, predicting the life expectancy from just the income. And that it seems like for at least these red guys down here off to the left, the fitted trend line with income to predict life expectancy, we're doing a better job. The line goes through where the data points are. And it's certainly not a whole lot worse up at this upper end, maybe even a little bit better than the average model. These errors should be smaller, yeah? Okay, so I'm going to go ahead and try my analysis again. And you know what I should just do? I should just, yeah, put this on top. Okay. And if I wanted to fit the model with just my income to predict life expectancy under fit model, you could also use fit y by x, but if you want, fit model is good. Life expectancy could be predicted by the income. And if I were to run that model, again, appears in the wrong place, but you know, here's your trend line, the regression line drawn in, and here is the residuals. And let's look at our friend so far. We've got our sums and squares total. There's a sums of squares that are explained by the model. 1943 is explained of the 3433. What is not yet explained is that 1490 error. Okay, there we go. The errors around this trend line, these vertical deviations, the sum of those guys squared is your 1419. That's the dashy cyan colored unexplained portion. What is explained by this cyan colored line, we're explaining 1942 of the total variability. What we can explain of the total variability is that chunk. In fact, you can say we're explaining 57% of the total variability in the data around the average. So far, so good? Okay, so if we were to switch gears and say, do we want to go to a model from a model of one trend line to a model of two trend lines, one for each group, one trend line for the red X's, the OPEC countries, and another trend line for the black triangles, the industrialized countries? I could go ahead and fit that model, and I did that for, okay, here we go. And let's go ahead and regenerate that model under fit model. We're going to say life expectancy could be predicted instead of just the income and life expectancy both. Run that analysis. And again, appears in the wrong place, but I can drag it over here and show you. Again, two parallel lines were fit. And my ANOVA overall portion says, well, we've got some model, if you will, or explain 2903 of their 3433. We're not explaining the 530. Let's I'll move it over here and this one a little bit to the left. Okay, so I think I can almost see everything I need to see here. What we are able to explain now with our model, our pink model is 29. Shoot, that's like 85%. Indeed, R squared 85%. We're explaining most of it. What is error not explained is still that 530. That's the 530. Okay. What we can explain with our pink model is an awful lot. What we can't is still error. The original model with the mean had a lot of error. We fit a trend line with income to predict life expectancy. We did pretty good. If we add in country type as well, we do even better. How much better do we do? That's the dashy bit in blue. That's how much gain we have from adding in country type. It seems like we're going to do better by adding in country type, yeah? Some of you are thinking, but that's because you put income in first. What if you did country type in first? Well, let's maybe go from our model where we have no country type, no income to explain, just one mean. Compare that green guy to our dark blue. How well is dark blue? Dark blue is doing really pretty well, huh? We're explaining an awful lot of the total variability. Let's look at that analysis, and I have that one lying around here. What is okay, that one. It's not the right one. Okay. Oh, no, I did have that right here. Yeah. Here is my ANOVA. My ANOVA is, again, the 3433 green total amount of variability. What we are able to explain with our dark blue line model, two lines, one for each group, it suggests here we're able to explain 2866 of the total, 2866, if you will, 83%. 83% of the former variability is now explained by which group you're in. And because in this model we have only country type, there's no slope shown. Income is not, according to this model, related to life expectancy at all. So our blue model is pretty darn good. Overall, we're explaining 83%. Do we do better to now add in a slope to allow both groups to have a different, to allow both groups to have a income relationship with life expectancy? If I again add in my pink model compared to my dark blue, the gain is very little. The gain is tiny. So pretty clearly it matters, because I've been able to say, well, income matters. It helps me predict life expectancy. And if I have income, adding in country type really helps a lot. If you add in country type first, you say country type really helps a lot. And then above and beyond that, income, we don't need it. Those are the two orderings we could go through. So let's get into our definition of sequential sums of squares. And that's really the key for the day and the key of the lab for the day. Inside JMP, by default, you get under your, under here, good. We have our parameter estimates. Notice that down at the bottom, you get these things called effects tests. It gives you a p-value for each of the two separate terms you're looking for. That is in adjusted sums of squares. And to understand what this analysis is doing, we have to tackle the question, which route did you take? Did you go for income first and then type of country? Or did you put in country first and then put in income? Under estimates, you could say, please show me my sequential tests. For sequential tests, there's two different orderings again that you could go through. And one of them is if you had, maybe I'll get rid of the plot. So focusing on here on the sequential test. If we had put in income first, how well are we doing explaining the total variability? And then secondarily, now when you add in the next term, how much does it explain above and beyond income being in the model first? That's if we put income in first, go to the, the income relationship with life expectancy first, and then add in type. If I had, however, an analysis like we had done, well, let's analyze fit model. We could have gone with the other ordering. Again, life expectancy, well, we could have put it in country type first and then income. Again, maybe it matters. I'm going to click run and note that, yes, it is over here on the other screen. Same model as we've been looking at before, two lines parallel. And if I go down all the way to the very bottom and say under estimates, show the sequential tests, our procedure says if we had type of country in first, that seems to explain an awful lot of the variability in life expectancy. But if we already had type in the analysis, does adding income help? I don't see it as helping. So the two different pathways, the two separate stories really are in these two separate analyses. Which did you put in first? Which did you put in first? Okay. So here's your formal definition. The first sequential sums of squares basically is SS for the model for that first variable. You put just one X variable into your model, the sums of squares for the model. That is your sequential sums of squares. Now, if you add a second term to your model, like we had income in first, and that added in country type, there's a change in SS error or SS model, a decrease in SS error, or if you will, an increase in SS model. The change in those terms, how much better off are we? How much do the errors go down by? That is your second sequential sums of squares. Your third sequential sums of squares, if we had a third variable in this analysis, would be if you already have a model with income and country type in it, would putting in also that third variable help you? How much does sums of squares decrease? Sum of squares error decrease, or how much does SS for the model go up? How much better off are we now by adding the new term? Okay. Each of these tests that are produced for us, these sequential sums of squares p-values, are conditional. Does that second variable matter if we already have the first one? Does the third one matter if you have both of the first two in your analysis? Sequential, that's how we define it. You choose the order, and you tell me how much better off when you go to step 2 from step 1 or step 3 to step 2. What about this adjusted sums of squares? It's JMP's default. It's the default of every stat package that I've ever met. That sounds like I've met stat packages, but you know what I mean. Basically, a stat package out there will use adjusted sums of squares. You probably have to go out of your way. Notice that I had to turn on sequential for my analyses. Adjusted, what you get by default is sequential, but last. Yeah, literally the adjusted sums of squares, using that for hypothesis testing, basically says, if you had already all of the other variables in your analysis, does adding this one in help us? Let's go ahead and verify that. I'm going to do that by dragging our friend over here off the side, and our two models here. The model where we have income in first and then type. If I show you these effects test, they are, what if we had income in first? And we put income first in our model, right? But if we had it, let me start over. Income, which is the first effects test listed, okay, in the adjusted sums of squares analysis. The default basically says, what if income were not the first term in the model, but rather indeed the second? What if income were the second one, but type was first? If type was first, then we're checking out the impact of income. This p-value for income is based on a sequential sums of squares of 36. We got that 36 right here. And we'd say, if you already had type in the model, does income help? I don't see it as benefiting. This effects test is sequential, but last. What about the sequential, I guess, but last, the effects test for type? That's a, well, what if income were first and then type were second? Well, in sequential, income comes first, then, oh, the sums of squares that's adjusted is the type of country sums of squares. Adjusted basically says, if you already had the other guy in the model, does this one help? No. If you already had the other guy in the model, income in the model, does type help? Heck yes. If we turn on the effects test in that other of the two analyses that we're comparing, again, it's giving us the exact same output as we had here, other than swapping the rows. Type, notice it's like a 960. It's in the second row here, but it's 960 with a F value of 45 and a P value of 0. Same deal. What about income? If income is in the second row in the adjusted sums of squares, it's just as if it were in the first row in the adjusted sums of squares. But if it's in the second row in the adjusted sums of squares, it means someone already fit a model with type in it. And because they fit the model with type in it first, the p-value and the f ratio in the sums of squares for income is, what if we add an income on top of a model that type already had, where type was already in our model? Okay, so our adjusted sums of squares is basically, you already have that one variable. I'm sorry, sequential is where you already have one variable, you add another, and then perhaps add in a third, a fourth, maybe even fifth. And as you go, you get a smaller and smaller error, or a larger and larger amount that the model explains. SS for the model should be growing. If we have a sequential analysis and something's in the last place in that sequential analysis, it says all the other variables, they've already been given their opportunity to explain what's going on with the response variable. Now, if those others have all failed in some way, but this new one can explain things, it will still end up proving itself. Our adjusted sums of squares does that for every single variable in your analysis. It says, okay, if this guy were last, and every other variable had a chance to prove itself first, would this one still be able to show itself as benefiting? Okay. Sort of a tough one, but I think it's a good place to perhaps, I think maybe it's a good place to stop after two quick examples. And one is a data set on poets. And I think our book has it in here, and I put it using it today. Here's data on a collection of famous poets, their year of birth, B year, their year of death, D year, and the poet's age at death. These data could have been collected to see if a person's age, or better yet, a poet's age, depends on when they were born. Because I think if people live longer over time, perhaps if the poet was born in 1298, they might die sooner than if they were born in 1922. Something like that. Okay. If I were to do my analysis, and I'm going to use fit model here. How does the age at death depend on the year of birth? Oh. Okay, there is my model. You're thinking that's a flat trend line. There's not much going on. Do we agree that R squared is about 0? We're not explaining much of anything with that flat trend line? Yep. The analysis of variance says, do any of the variables seem to help us at all? The answer is no. Now, let me ask you a question. If you have the birth year and the death year of a poet as explanatory variables, could you predict their age, death, the poets? Let's go ahead and try that analysis. This is where, like, a regular classroom is better, because someone in a regular classroom would have done what I was sort of hoping one of you would do and unmute. If I have birth year and death year both in the model, do you think you could predict the age at death? I was hoping one of you would just type duh into the chat. Okay, so let's go ahead and look at what is produced as our analysis. The slope for birth year and death year looks suspiciously like 1 and -1. So death year times 1 minus birth year times 1. That'd be just the year of death minus the year of birth. Helps me predict the age at death, right? How well are we doing? We're able to explain 99.9% of the variability in ages at death based on those two variables alone. Either variable by itself, birth year, doesn't help me. That's a flat trend line. Death year alone really doesn't help. But between the two of them, oh my gosh, adding in the extra variable of death year all of a sudden clarifies that relationship between birth year and the poet's age at death. Yeah? What was unclear now is very clear. Let's try a different data set, and this is the last one, and it's legs. And here's a fun data set because it's the weight in kilograms of a collection of humans and the length in meters of their right leg and their left leg. Okay, so weight in kilograms predicted by left leg length or right leg length. And you tell me, do you think you could predict the weight of someone based on their leg length? And because I'm staring at my screen and not looking at the two of you who are, with the camera on, I can't tell, but some of you are thinking, let's look at the graph. Go ahead, analyze fit model. Boom. Boom. If I say weight, could I predict it? And I'm going to go with left leg length for fun. I could have put in right leg length just as easily. Does it look as though there is a relationship? Is this left leg length helping me predict weight? I'd say so. How well are we doing overall? Our value of R squared is like 56%. That's pretty good. Is left leg length helping me predict? My p-value, my ANOVA says yes. My effects test by adjusted sums of squares, p-value says yes. In fact, they're the exact same thing. One explanatory variable gets us the ANOVA for the whole model equals the effects test ANOVA. What if we changed it up in the last 37 seconds and say, what if we want to fit another model where we're not using just left leg length to predict weight, but we added in the right leg length as well. Run that up here. And here's the thing that's a challenge at first to grab onto. Notice that our squared is a little bit better than before, from 56 to 57%. Yeah, a little bit better. I don't need that graph, but I do think the effects tests is curious. I'm going to read these off and then we'll call it a day. If I already have right leg length in the model to predict a person's weight, does adding in their left leg length help me? No. Let's try it a little bit differently. If they already have their left leg length in the model to predict their weight, does adding in the right leg length help me? No. Would one or the other variable be helping me about the same to predict a person's weight? My guess is yes. You might be wondering why. It should be obvious after I produce the graph. You think I could produce a graph? No. Do you think you can predict a person's left leg length from their right leg length? Are these leg lengths, are each of them producing essentially the same bit of information? In most every case, they're almost exactly the same. So having the new variable saying, hey, I already had right leg length in the model, is having left leg in the model help me? The answer is no, it doesn't. You already have something that's enough. Okay, good place to stop. I think I've introduced the concept of sequential sums of squares. You're going to tackle a lab involving it between now and shoot next time. And next time we'll have a fairly healthy discussion on what exactly sequential sums of squares does. And we'll get a little bit deeper into the topic of multiple explanatory variables. But that's for after the lab. So I'm going to stop the share. And if you guys have any questions, I'm happy to tackle them. Otherwise, I'm going to stop the recording and say mañana, which I've heard is Spanish for tomorrow.
Sorry, quick question. Are we supposed to have access to the second 3A on the homepage? Or just the first one?
No, I don't think so.
Okay.
But just the first one, and I've been doing editing as we've been going, and I forgot to change the name of that, but that's going to be Experimental Design, Chapter 5. Whereas last time I did it, it was like 2 separate topics in 1 week. This time we're sort of having them in the 2 separate parts of the same week, but it's broken down a little differently.
Okay. All right. Thank you.
Mm-hmm.